Bismillahirrahmanirrahim. This is Jahangeer Soomro, Assistant Professor, Electrical Engineering Department, Sakkaraib University. Today I will discuss one of my review article, which is having title of a detailed review on MMC circuit topologies and modeling issues. MMC is a promising technology for MTDC systems and would transform into the concepts of supergates in the near future. Yeah, this is true. MMC, after its successful implementation in high voltage DC transmissions, now for the future power system, we are moving from HVDC to multi-terminal DC systems where there are more than 2 converter stations in multi-terminal DC systems. So again, scientists are focusing and emphasizing towards the use of renewable energy, such as wind power plants, such as solar. So with these renewable energy integration, the importance of multi-terminal DC systems is increasing, and MMC-based MTDC systems are preferred recently. And yes, they are transforming towards the concept of supergates, where recently some projects are under consideration, where intercontinental grids are being visualized, such as Asia-Europe grids. This field will move towards supergates, MMC-based multi-terminal DC systems, and then this concept will move towards the supergates, in which different intercontinental gates are possible in the future. All right, the silent features of modular multi-level converters. Now this modular multi-level converter is the latest, is the most advanced converter in the form of VSC. So this is the latest generation of voltage source converters, MMC. All right, modular multi-level converter is preferred in this area of HVDC because of its silent features such as modularity. Now, what does modularity means? Modularity means that you can increase or decrease number of cells or sub-modules. Cell is a basic building block of modular multi-level converter. So as per the need and requirement of the application, cells can be inserted or removed. In simple words, combining smaller subsystem to make a larger system is known as modularity. So in terms of MMC application, smaller submodules or cells are combined together to get high power and voltage rating. So this is modularity. So with more number of submodules, certainly the number of power switches will increase. So it will have reduced dV over dt and di over dt stress on switches as compared to 3-phase 2 level, which cannot handle high voltage and power ratings. So if you try to use a 3-phase 2 level which has just 6 switches for the HVDC application, so these 6 switches will not be able to afford the dV over dt and di over dt stress. So in other words, those 6 switches will damage for the HVDC application. So certainly we need to move towards higher number of submodules and more switches. So in this way, MMC has this feature that it offers reduced dV over dt and di over dt stress on the switches, because more number of submodules and more number of transistors are used. Voltage and power scalability, as discussed, the number of submodules can be increased and decreased as per the requirement of power and voltage. Moreover, it has fault blocking capacity. Yes, MMC can block the converter faults, including a very serious and critical fault such as DC pole-to-pole short circuit fault. DC pole-to-pole short circuit fault is considered to be very dangerous and very critical fault in the field of MMC HVDC when the 2 DC links are short circuited. In this condition, it can be very high fault current can flow, which can damage entire system including converters. But the good thing is that MMC has this capability to block this fault. How? We can discuss later on in the next discussion. All right. Not only DC Seaver fault, but MMC can also block other AC faults such as symmetrical and asymmetrical faults. In the case of MMC HVDC, the faults may occur at the rectified side or gate side, or it may occur at the load side or AC side. So in these both conditions, AC faults and DC fault both can be mitigated, can be handled. The another good feature of MMC is fault blocking capability and fault right through capability. So due to this feature, MMC is very considered to be a very robust topology. All right. Okay. Transformerless operation is possible with MMC and improve power quality. No doubt, if you increase the number of sub-modules, maybe let us say I consider n is equal to 50. So with conventional nearest level modulation with MMC, with when n is 50, so you are going to get 51 levels. So 51 levels, if you try to check the FFT 51 level output voltage, you will see that harmonics will be expected to be below 5%. So without the need of any filter, you can get better power quality in case of MMC, and this is one of the very attractive feature that the filter losses can be avoided. So therefore, researchers prefer to use MMC. All right. Despite of these all advantages, there are some technical issues and challenges to be critically analyzed and addressed, such as here I would like to address only 2 problems, but the problems can be more than that. One technical issue is circulating current. Now in case of MMC, circulating current flows. Circulating current basically consists of 2 components. One is a DC component, which is IDC by 3, which is desired, which is required. But the AC component of the circulating current, which is twice the fundamental frequency, and this component needs to be eradicated because if this circulating current is not suppressed and eradicated, then the problem will be that it will trigger. It majorly consists of second harmonic. The circulating current, mainly the dominating component is the second harmonic, but if it is left uncontrolled, then it can trigger towards 4th harmonic, 6th harmonic, 8th harmonic and onwards, and in this way the overall system can collapse and your overall system can damage, overall power quality can be problematic. So therefore, if the circulating current is not properly suppressed, then again this will lead towards the problem of capacitor voltage ripple problem, because in MMC consists of cells, and every cell there are capacitors. Basically, if you see the equation of the capacitor, we will find out that capacitor consists of one DC component which is desired, but there is also some ripple component available in the capacitor. So if the circulating current is not properly controlled, this ripple component of the capacitor will increase, and result, if this ripple component is increased, then certainly this will be problematic situation and power quality will be compromised. So therefore, circulating current must be suppressed. Moreover, another challenge in the MMC is capacitor voltage balancing problem. Yes, in case of MMC, as compared to other power converter topologies, it has more capacitance. So more capacitance can have advantages in some scenarios, like these capacitance may be used in power oscillation damping, or may be used to mitigate the problem of voltage sag if it occurs on the rectifier side. So these are some possible advantages of high capacitance, but again, having high capacitance can be challenging because you need to balance out all the sub-module capacitors, and overall the arm voltage capacitance and leg voltage capacitance should be balanced. So voltage capacitor balancing is another technical challenge. Similarly, there are also other challenges which we'll discuss maybe in later stage. All right. So there's the room for development of novel and enhanced MMC based on sub-module configuration to enable higher efficiency, power quality, compactness, and DC fault blocking capacity. All right. So some researchers are working in the area of proposing the enhanced modular multi-level converters, which offer higher efficiencies, which offer improved power quality, which offers compactness. Let me explain this point in a little bit detail. Conventionally, with conventional nearest level modulation, basically this thing need to be understood that if you want to control the output voltage and current of the converter, you need some pulse width modulation technique. And Pwm techniques or pulse width modulation techniques are basically classified into 2 types. One is the high switching frequency techniques. One are the high switching frequency techniques like sinusoidal pulse width modulation, carrier phase shift, and others. Others are the those PWM techniques which operate on fundamental switching frequency, such as nearest level modulation. So in terms of HVDC application where number of submodules are very high, maybe n is more than 20. So in these cases, mostly nearest level modulation technique is preferred because it will offer low switching losses. Reason being that it operates on fundamental switching frequency 50 Hz. So but in a conventional NLM, if it is nearest level modulation, but if it is conventional, if you are using n number of submodules or n number of cells, then it will offer you n plus 1 levels. So if the number of submodules are maybe 20, then the levels will be 21. But if you are moving towards some modified nearest level modulation techniques, then it is very possible some researchers have obtained 2n plus 1 levels. So if the number of submodules is 20, 2n plus 1 means that 41 levels are possible. But if the number, like in our research work, in my PhD research work, we have proposed some modified nearest level modulation techniques, which can be found in our other research papers, where we have proposed that 4n plus 1 levels can be also achieved with some modification in this nearest level modulation techniques. So with 4n plus 1 means that if the number of submodules are 20, that means 4 into 20, 80. 80 plus 1 means 81 levels are possible with 4n plus 1 levels. So see the advantage. Without increasing the number of switches, n is same, but you are getting more number of levels. More number of levels means that the waveform will be now more closer to the sinusoidal waveform. That means that improved power quality will be offered without increasing the number of switches in some modules. So it will result into compactness. So this is how some researchers are also working in this area to improve the efficiency, improve power quality, and compactness. And moreover, DC fault blocking capacity. Like I already discussed, that DC pole-to-pole short circuit problem is a very critical and very challenging issue. So this must be addressed. So researchers are also working in this area, where like some of the researchers are proposing some variants of half-bit submodules, where they suggest that DC fault issue can be cleared. DC fault clearance issue techniques are suggested. Like some researchers are suggesting full bridge based submodules for MMC based HVDC systems, because full bridge submodules, DC fault can be blocked and can be cleared. So DC fault blocking capacity is another important feature of MMC. Moreover, developments of efficient and accurate modulars required for the studies of MTDC grids during steady state and transient conditions. This is very true. As per SIGRI, there are 7 types of models which are used. All right. So not every model is perfect for every situation. Literature reviews suggest a need for studying and comparing different MMC modeling approaches, because no modeling technique can be best suited for all applications. Suppose if you want to analyze internal submodule fault of MMC, you want to see if there is any flashover problem, if there is any damage of the internal submodule capacitor issue. So if your focus is internal submodule, so in this case detailed switch modeling or type 1 can be preferred and can be used for the studies. But if your object is to power system studies or network flow studies, then aggregate or average modeling can be used. So where to use which modeling technique is a question, and this question is also discussed in this review paper, that which modeling technique is better for what applications. Okay, so this is also addressed. The main contribution of this paper is to provide a comprehensive review of recent developments in MMC in terms of submodule configurations. Various submodule configurations are discussed in this paper. Moreover, this paper also presents an in-depth review of systematic comparison of different models of MMC from type 1 to type 7. These models are discussed, compared, which researchers have used which models and why. These questions are discussed in the paper, which can enable appropriate selection of model based on target studies and desired accuracy and efficiency. Finally, the associated research challenge and future trends are presented. So this was about abstract. In the next part, we'll discuss introduction. Thank you very much.